Imagine this. You walk into a room, it's dark, right? And with just a simple flick of a switch, boom, light floods the space. It's so commonplace, so second nature. We rarely, if ever, stop to think about the intricate sort of invisible system making that everyday magic happen. It's this whole network of components and carefully planned circuits that quite literally bring our built environments to life. Today here on The Deep Dive, we're pulling back the curtain on that seemingly simple act. We're embarking on an in-depth exploration of artificial lighting and circuit layout. And this isn't just about the light bulb itself, It's about understanding the foundational elements that illuminate our entire world. Everything from the tiniest light-emitting components to the surprisingly intelligent controls that dictate how and when light appears. Our sources for this deep dive come directly from these incredibly detailed notes on interior construction and utilities. It gives us a real architect's perspective on the matter. And for you, our listener, understanding these behind-the-scenes details can fundamentally transform how you perceive your own home, your office, or really any built environment you walk into. It's about gaining quick yet incredibly thorough insight into something utterly essential that we largely take for granted. I'm truly fascinated by how something so fundamental, something we interact with dozens of times a day, reveals just layers of complexity and, frankly, ingenuity once you start to unpack it.
It's absolutely true. And these details, while they might seem a bit technical on the surface, they translate directly into very practical implications for our daily lives. Understanding these systems isn't just some academic exercise. It's really about grasping how they impact everything from a building's overall energy efficiency and safety to the very mood and functionality of a space. It's all interconnected in ways that, once you understand them, it really does redefine your perception of the illuminated world around you.
Okay, so to really dive deep here, we need to establish a common language first. Seems sensible. We hear terms like lamp and luminaire thrown around, sometimes, interchangeably, but our sources say there's a crucial distinction. It seems pretty foundational to understanding lighting designs. What exactly sets them apart?
That's an excellent starting point because, in lighting, precision really matters. When we speak of a lamp, we are referring specifically to the component that actually produces the light. So the glass bulb or tube that emits light when electricity passes through it. Think of it as the actual light source, the part that glows. Historically, this was the filament, in an incandescent bulb. Now it might be an LED chip or a gas discharge tube in a fluorescent.
Okay, so the lamp is the light generating core.
Mm-hmm.
The bit that makes the light. But a light fixture, as most people understand it, is more than just a bulb, right? It's the whole thing hanging from the ceiling or mounted on the wall.
Absolutely. And that's precisely where the term luminaire comes in. A luminaire is the complete lighting unit. It encompasses the lamp, or sometimes multiple lamps. But crucially, it also includes all the other parts designed to distribute that light effectively. This means elements like reflectors that direct light, diffusers that soften it, maybe lenses that focus it, even specialized optics that can shape the light beam.
Ah, okay. So it's not just holding the lamp.
Not at all. Beyond light distribution, the luminaire also includes components for positioning and protecting the lamps, making sure they're held securely and shielded from things like dust, moisture, or even physical impact. And of course, it contains the necessary electrical components to connect the lamps to the power supply. Things like ballast for fluorescent lamps or drivers for LEDs, which manage the power flow correctly.
So the luminaire isn't just a fancy housing, it's actually an engineered system. It transforms the raw light of the lamp into controlled, usable illumination. Its design directly impacts light quality, like reducing glare, creating specific beam angles, maybe even managing heat generated by the lamp. This sounds far more sophisticated than just, screwing in a bulb.
Precisely. And for our listeners, consider this. A bare LED chip might be incredibly efficient at generating photons, generating light, but without a well-designed luminaire, which includes its optical components and, importantly, thermal management, that raw light can be harsh, glary, or just inefficiently distributed. The luminaire transforms that raw light, shaping its beam, its color temperature, even potentially its flicker rate, all of which are critical for visual comfort and, task performance. This is why I say a simple recessed downlight can look and perform very differently than maybe a decorative pendant light, even if they technically use the same type of lamp inside.
Okay, that makes sense. Now here's where it often gets confusing for, pretty much anyone who's ever stood in a hardware store aisle trying to pick a new bulb.
Mm-hmm.
We used to just look at watts, right? Thinking higher watts meant brighter light. Simple.
Yeah.
But now it's all about lumens. What does this fundamental shift mean for us, the consumers, when we're trying to light our homes or offices effectively?
Yeah, this shift from primarily looking at watts to focusing on lumens is a really pivotal change. It's driven largely by the advancement of all these energy-efficient technologies we're seeing now. Historically, watts measured the amount of electrical energy a light bulb consumed every hour. Simple enough. So a 100-watt incandescent bulb used 100 watts of power per hour. However, and this is the key bit, wattage tells you basically nothing about how much light you're actually getting. It's a measure of energy consumption, not light output.
That's the key distinction, isn't it?
Mm.
I remember my old 60-watt incandescent bulb seemed bright enough. But a modern LED bulb can achieve the same, maybe even greater brightness with, what, like 10 watts? Maybe even less sometimes.
Exactly. With the rise of energy-efficient options like LEDs, a bulb might only use, say, 8 or 10 watts. But it can produce the same amount of light, or often even more light, than an old 60-watt incandescent. That's precisely why lumens became the standardized unit of measure for how much light you are getting from a bulb. It's the total light output of the source itself, regardless of how much power it consumes. So when you're buying a bulb today, you should always be looking for the lumen output, not just the wattage, to understand its brightness. For instance, a common 60-watt incandescent equivalent LED bulb will typically produce somewhere around 800 lumens. That's the number to look for.
Okay, so lumens tell us the total light pumped out by the lamp.
Yeah.
But the light leaving the bulb isn't necessarily the same amount of light that's actually hitting your desk or illuminating your workspace, right? That brings us to another term mentioned in our sources, illuminance.
You're keenly observing the next crucial layer of lighting design, yeah? You have the light source's total output, measured in lumens, okay? Then you have illuminance, which is the amount of light actually falling onto or illuminating a given surface area. This is measured in lux, which is technically lumens per square meter, or sometimes foot candles in the US, which is lumens per square foot. If we connect this to the bigger picture, understanding both lumens and illuminance is absolutely key to designing effective lighting that meets specific functional needs. For instance, a general office space might require, say, 300, 500 lux on the work surfaces for comfortable working conditions. But a really detailed task, like maybe drafting or fine assembly, might need much more, maybe 750, 1,000 lux. Ambient lighting for just walking through a hallway, however, might only require 5,100 lux, much less.
So it's not just about how bright the bulb is, lumens, but how effectively that light is delivered and spread across the surface, lux, and tailoring that to the specific activity. That's actually a profound insight for anyone setting up their home office or even just choosing a good reading lamp.
Precisely. And this knowledge genuinely empowers consumers to make much better, more informed choices. Not just about brightness, but also about how much energy they're consuming and how functional and visually comfortable their spaces will ultimately be. It moves beyond simply more light is better to thinking about the right light for the right purpose. This also ties into the concept of efficacy, which you sometimes see listed. That's lumens per watt, basically, how efficiently the lamp converts electricity into light. A high efficacy number, like maybe 100 lumens per watt for a good LED, is far more efficient than, say, 10 or 15 lumens per watt for an old incandescent. You're getting much more light for your energy buck.
Okay, got it. So all this electrical magic, the power for these lumens and lux, has to start somewhere. It can't just, float in from the ether. Where does all the power originate within a building?
Yeah.
How is it channeled into these circuits we'll talk about later? That's the domain of the panel board, right? Which our sources describe as feeling like the central nervous system of your entire electrical setup.
It absolutely is. That's a great analogy. And this raises an important question about both safety and centralized control within a building's electrical infrastructure. The panel board is defined as a fundamental component of an electrical distribution system. You'll find one in pretty much every building. Its primary role is to take the main electrical power feed, which typically comes in from the utility grid outside, and systematically divide it into various smaller, more manageable branch circuits.
And it's not just about splitting the power up, is it? There's a really critical safety aspect built right into its function. It protects the whole system and the people inside the building.
Indeed, that's arguably its most critical function for each of those branch circuits it creates. The panel board houses a protective circuit breaker, or in some older installations, you might still see fuses, all contained within a common enclosure, usually a metal box. This is the critical safety hub. Think of each circuit breaker as a sort of guardian for its specific branch circuit. the wiring going to your lights, your outlets, etc. If there's an overload, meaning too many devices drawing too much current on that circuit, or if there's a short circuit, which is a dangerous fault in the wiring, that circuit breaker will automatically trip, cutting power only to that particular branch, instantly. This prevents a localized issue, like faulty wiring in one room, from escalating into larger, much more dangerous problems like electrical fires or, widespread power outages within the building. It effectively isolates the problem.
So it's basically the intelligent gatekeeper, preventing a small problem from becoming a huge one, potentially a disaster, like a fuse blowing, but resettable. And its physical location within a building, as mentioned in our sources, seems incredibly important too, not just stuck in any old closet.
Its location is, in fact, crucial and usually dictated by electrical codes. Our sources emphasize that the panel board is often placed on the ground floor, or sometimes in a utility room or basement, but always in a location where it can be readily seen and, most importantly, easily accessible in an emergency. Imagine a sudden power surge or you smell burning plastic. You need to be able to quickly and safely get to that panel to cut off power, either to the affected circuit or potentially the main breaker for the entire building. Being able to get to that panel board without scrambling through a dark, cluttered basement or an inaccessible attic crawl space is a fundamental aspect of building safety and emergency preparedness. Electrical codes, in fact, mandate specific clearances around panel boards, usually about 3 feet of clear space in front and 30 inches wide, to ensure unimpeded access for both routine maintenance by electricians and, critically, for that emergency response. Its design and placement are meticulously planned to allow for quick access and control during any power-related issues, ensuring the building occupant's safety and the integrity of the whole electrical system.
Okay, fascinating. So now that we know the basic terms, we've got lamps, luminaires, lumens, and we know the power starts at the panel board. Let's shift our focus. Let's talk about the actual stars of the show, the lamps themselves, the light makers. We've witnessed a truly monumental evolution in lamp technology, haven't we? Moving far beyond just the old, familiar incandescent bulb that, well, many of us grew up with.
And this evolution has had a profound, often understated impact on how we light our spaces, especially in commercial, industrial, and even increasingly in residential settings. Let's start with what was, for decades really, the workhorse of many larger buildings.
The fluorescent lamp.
Yeah, when I think fluorescent, I definitely picture those long tube-like lights, in every office building, school hallway, or grocery store ceiling. What made them so ubiquitous for so long? You're right, fluorescent lamps became incredibly common. They're used to provide broad illumination for commercial, industrial, classroom, and retail lighting. And the main reason was their efficiency compared to the older, traditional incandescent bulbs they replaced. They work through a slightly complex process, passing an electric arc through a noble gas, usually argon, and some mercury vapor inside the tube. This excites the mercury atoms, which then emit ultraviolet, or UV light. You can't see that. But this UV light then hits a special phosphor coating on the inside surface of the glass tube, causing that coating to glow, or fluoresce, in visible light. This multi-step process makes them far more efficient than incandescents, which basically just heat a wire until it glows. Fluorescents convert a much higher percentage of electrical energy into visible light rather than just wasted heat.
Okay, so a big leap in efficiency over the old incandescent bulbs. That makes sense for big buildings using lots of light. Did they offer much variety beyond just those, standard long tubes?
Oh, absolutely. Fluorescent lamps actually vary significantly in size, light colors, and wattage. You have the long linear tubes, like the T8s or T12s you often see, but also U-shaped tubes, circular ones, and compact forms, which we'll get to. And the color of light, or color temperature as it's called, measured in Kelvin K, is also crucial. Fluorescents come in a wide range. You can get cool white, maybe around 4100 K to 5000 K, which provides that crisp, almost bluish light often associated with productivity in offices. Or you can get warm white, down around 2700 K to 3000 K, which has a more yellowish incandescent-like glow, often preferred in retail or hospitality. This versatility allowed designers to tailor the light to different environments and tasks. However, it's worth noting early fluorescents often suffer from noticeable flicker, which could cause eye strain or headaches for some people, and they also contain a small amount of mercury, which poses disposal challenges. You can't just toss them in the trash.
Right, the mercury thing. I remember hearing about that. And then, for those of us who remember, came what felt like the first real green alternatives we started putting into our homes. The compact fluorescent lamps, or CFLs, the curly ones. Oh yeah, I remember those. They seem to pop up everywhere. A direct assault on the old incandescent.
Yes. CFLs represented a very significant step towards energy efficiency, specifically aimed at residential settings. They effectively bridged the gap between traditional incandescent bulbs and the even more efficient LED technologies that were coming down the pike. As our sources note, they were generally designed as direct screw-in replacements for incandescent or halogen lamps. This made the transition incredibly easy for consumers. You just unscrewed the old bulb, screwed in the CFL. The source material highlights two major types: the screw-in ones, which allowed for that direct swapping into existing sockets and fixtures, and also plug-in types, which had pins instead of a screw base, often used in more specialized commercial or decorative fixtures, like some recessed downlights or desk lamps.
The screw-in CFLs really were the game changers for homeowners, weren't they? Suddenly you didn't need special fixtures. Just swap out your old energy guzzler.
Precisely. That versatility, particularly with the screw-in type, made CFLs a critical bridge technology. It truly helps shift consumer habits and perceptions towards energy-saving lighting alternatives on a really widespread scale. They introduced the idea to the average homeowner that lighting could be both effective and dramatically more energy efficient. However, they also had their drawbacks, as many people experienced. Many had a noticeable warm-up period before reaching full brightness. Some produced a light quality that people found less appealing than incandescent. And their dimming capabilities were often limited, sometimes problematic, causing buzzing or flickering. And like the traditional linear fluorescents, they also contained small amounts of mercury, necessitating careful recycling or disposal.
Yeah, the warm-up time and the dimming issues were definitely things I remember. Okay, and then here's where the lighting revolution truly accelerated, right? Light-emitting diode lamps, LEDs. They have completely, utterly changed the game, not just for efficiency, but for how we design, control, and even think about using light in virtually every application imaginable.
This really raises a fundamental question. Why are LEDs so transformative? What makes them such a leap? Well, our sources clearly state they are significantly more energy efficient than equivalent incandescent lamps, often by a staggering 80–90%. That's huge. And they're even considerably more efficient than most fluorescent lamps, too. This isn't just a slight improvement, like going from 15 milliamp to 20 milliamp in a car. It's a monumental leap in efficacy, delivering far more lumens per watt. This translates directly into substantially lower electricity bills for consumers, businesses, cities, and a dramatic reduction in global energy demands for lighting overall. Just consider the impact of retrofitting an entire city's streetlights or a massive office building or millions of homes with LEDs. The cumulative energy savings are immense.
And beyond just the raw energy savings, they seem to last practically forever. And they offer incredible design flexibility. We're seeing lights and shapes in places we never thought possible before.
Indeed. That's the other side of the revolution. If we connect this to the bigger picture, LEDs also offer unparalleled longevity. They often last 25,000 to 50,000 hours, maybe even more in some cases. It's many times longer than fluorescents and literally hundreds of times longer than incandescents. This dramatically reduces maintenance, costs fewer bulbs to buy, less labor changing them, especially in hard-to-reach places. But the true game changer, the profound aha moment for designers and architects, is the unprecedented control and design freedom that LEDs offer. Because LEDs are solid-state devices, basically tiny semiconductors, and they naturally emit light in a specific direction, unlike bulbs that throw light everywhere. They don't necessarily require bulky reflectors or diffusers in the same way traditional sources do. This allows for ultra-compact form factors. Think incredibly thin light panels, flexible light strips that can be bent and integrated right into architecture, under cabinets, along stairs, and even individual light points the size of, well, a grain of rice.
Wow, that level of granular control must open up incredible possibilities for creating dynamic, responsive environments, not just static light anymore.
Exactly. LEDs enable dynamic lighting in ways that were previously very difficult or expensive. This includes tunable white light, where you can shift the color temperature from a cool, invigorating blue-white light in the morning, like daylight, to a warm, relaxing amber-white light in the evening, mirroring natural light cycles to potentially support human circadian rhythms and well-being. They also allow for full-spectrum, color-changing capabilities. Think mood lighting, branding, entertainment effects. Plus, precise dimming down to 1% or even less, often without the flicker or hum associated with older dimmable technologies. This really moves light from being just a utility, just illumination, to becoming an intrinsic dynamic element of architecture and interior design. And we're seeing LEDs integrate seamlessly into smart home and smart city systems, offering app control, voice assistant integration, occupancy sensing built right in, and even exploring things like data transmission through light, a technology sometimes called Wi-Fi. The long-term impact on global energy consumption, architectural design, design freedom and even potentially human health and productivity is still unfolding, but it is undeniably revolutionary. It's a whole new era for lighting.
Okay, so we've got a handle on the different lamp types, the luminaires they go into, and how we measure their output.
Aha.
Very cool. But once you know what kind of light you want, how do architects and designers actually figure out how much light a room truly needs and where all the fixtures should go? It's clearly not just guesswork, right? They don't just sprinkle lights around randomly.
You're absolutely right. It's a very methodical process, especially in professional design. And one of the foundational tools, particularly in the preliminary design stages when you're figuring out the general ambient lighting level, is what's called the simple lumen method.
Okay, the name simple suggests it's maybe approachable, but it still sounds like a technical calculation. And the phrase maintained illuminance also stands out in the description. What exactly does this method entail, and why is that maintained aspect so crucial?
Yeah. The simple lumen method provides a practical, sort of foundational procedure for determining the average maintained illuminance on the working plane in a room. The working plane is usually considered a horizontal surface about desk height, maybe 30 inches off the floor. It's considered simple because it's an average calculation across the whole room. It gives you a good estimate for general lighting levels. Assuming that the luminaires, the fixtures, will be spaced appropriately to provide reasonable uniformity of illumination across that space. It's not typically used for highly specialized or task-specific lighting, like highlighting artwork or providing intense light for surgery. But for achieving a good baseline of consistent general light, it's highly effective and widely used.
Okay, and the maintained aspect. Does that account for the fact that lights don't stay perfectly bright forever or that fixtures get dusty?
Precisely. The maintained aspect is absolutely critical because it accounts for various factors that reduce the actual light output delivered to the room over time. Real-world conditions. This includes things like lamp lumen depreciation, LLD, which means that pretty much all lamps, even LEDs, naturally get dimmer as they age. They don't just suddenly burn out usually, they fade. And it also includes luminaire dirt depreciation, LDB, which accounts for the inevitable accumulation of dust and dirt on the lamp itself and on the luminaire's reflective surfaces or lenses. Both reduce light output. By designing for maintained illuminance, architects and engineers are ensuring that even after a certain period of use, and some inevitable light loss, for instance, maybe after a year or two of operation between cleanings, the light level in the room will still meet the required minimums for its intended purpose. It's a pragmatic approach, building in a buffer for reality. It's a key tool for preliminary design, especially when maybe the exact make and model of the luminaire hasn't been finalized yet. But you need to estimate the number of fixtures early in the planning process. So, for example, an architect might use this method to calculate that a 400 square foot office needs, say, 500 lux of maintained illuminance. Then factoring in the expected lumen output of a typical fixture and applying these light loss factors, LLD, LDD, etc., they can calculate that they need maybe 10 2x2 LED panel luminaires to achieve that uniform baseline over time.
Got it. So it's planning for the long haul, not just day one brightness. Makes sense. Now, once you've calculated how much light you need and roughly how many fixtures, the next huge step is actually powering it all up, getting the electricity safely and efficiently to the right places. This is where the electrical blueprint comes in, detailing the lighting branch circuit layout. This really is the hidden backbone of our lighting, isn't it? The veins and arteries delivering the electricity throughout the building.
That's an excellent analogy, yeah. The guidelines for lighting branch circuit layout that are in our source material, they are essentially the foundational rules for how that electrical backbone is designed and installed. They ensure both functionality and, critically, safety and adherence to stringent electrical codes like the National Electrical Code, NEC, in the U.S.
Okay, let's walk through these guidelines from the source. Some of them sound like, basic good practice, but some are surprisingly specific, like that limit on how many lights can actually be on one single circuit. That caught my eye.
Let's delve into each one because there's a solid reason behind each step. First, the guideline says you prepare the electrical symbol list or the legend on the blueprint. This is absolutely vital for clear, unambiguous communication on construction plans. You need everyone reading the same map. Different symbols represent different electrical components, various types of switches, outlets, different kinds of luminaires, recess, surface, pendant, etc. Using standardized symbols, like those from IE or ANSI in North America, ensures that everyone involved in the project, from the architect and engineer to the electrician doing the installation and even the building inspector signing off on it, understands precisely what each element on the blueprint represents. This minimizes costly errors or dangerous misinterpretations during construction. Second, the guideline says you locate the electrical panel board on the plan, as we discussed earlier. It's often on the ground floor or in an accessible utility space where it can be readily seen and easily accessed in an emergency. Its strategic placement is paramount. Codes mandate those clearances around it, typically 3 feet clear in front, 30 inches wide, to ensure safe access for work and emergencies. It's a non-negotiable safety requirement.
Right, so that central nervous system, the panel board, needs to be clearly marked and readily available. Makes sense. What's the next step for actually laying out the circuits themselves, connecting the lights?
The third guideline gets into load management. You count the total number of lamps, or more accurately, lighting fixtures per floor. And then you group these fixtures together onto specific circuit lines following a specific guideline mentioned in our source. A maximum of 12 lights or fixtures per circuit. Now, this is where some core electrical engineering principles come in. This 12 lights figure isn't just an arbitrary number someone picked. It's a critical safety measure aimed at preventing circuit overloads. Most standard residential branch circuits are protected by either a 15-amp or a 20-amp circuit breaker. If you put too many lights, or maybe just a few very high wattage lights, onto a single circuit, they could collectively draw too much current. Amperage. That excessive current can overheat the wiring inside the walls, potentially melting insulation and creating a serious fire hazard. It will also reliably trip the circuit breaker, cutting power. Limiting the number of fixtures per circuit helps ensure that the total load stays well below the breaker's rating. It enhances system stability. It also prevents huge sections of a building from losing power if just one small area experiences a fault and trips its breaker. And it helps prevent excessive voltage drop over long wire runs, which can cause lights at the end of the circuit to appear dim or make certain appliances run less efficiently. It's worth noting, though, with modern very low wattage LEDs, the 12-light rule is perhaps more of a general rule of thumb from the era of higher wattage bulbs. The actual limiting factor today is often the total calculated amperage drawn by all devices on that circuit, which must not exceed 80% of the breaker's rating for continuous loads like lighting, according to code. But the principle of limiting the load per circuit remains crucial.
Wow, okay. So it's really about protecting this system, protecting the occupants from fire hazards, and even ensuring the lights work properly. I imagine many listeners, myself included probably, have maybe inadvertently overloaded a circuit at home without realizing it, perhaps by stringing up way too many old-style holiday lights, or running a space heater and a vacuum cleaner on the same outlet. This really makes you think about those hidden electrical limits.
It absolutely does. Those breakers are there for a very good reason. And finally, the fourth guideline is about connectivity and routing. You physically connect the lamps or fixtures together on the plan for each circuit. And crucially, on the end lamp of every circuit run, you draw what's called the circuit home run. This is typically an arrowed line drawn from the last fixture back toward the panel board location on the blueprint. These home runs represent the main electrical paths, the wires that carry power from the panel board out to that string of lights. And, just as importantly, they represent the path carrying the return current back to the panel board to complete the electrical circuit. You always need a complete loop. They show the literal connection back to the power source and the breaker. If we connect this to the bigger picture, these meticulous planning guidelines, the legend, the panel location, the load limits, the home runs, they demonstrate the incredibly detailed and precise work required. It's all to ensure both functionality and, most importantly, safety in a building's entire electrical system. It's this complex dance of power distribution, protective measures, and clear communication on paper, all designed to make that simple flick of a switch work flawlessly and safely every single time.
Okay, fantastic. So we've got the power source figured out at the panel. We understand the different lamps and luminaires. We know how light is measured, and we see how the circuits are carefully planned and laid out. But how do we actually control the light? This is where switches come in, obviously. And based on our sources, there's far more variety and sophistication here than you might initially think. It goes way beyond just a simple on and off.
You're absolutely right. Light switching, as the source material puts it, pertains to the provision of control devices that turn on or off, or sometimes dim, a particular lamp or a set of lighting fixtures. And what's truly fascinating here, as you said, is how these devices have evolved. They've gone from those very simple binary mechanical toggles to incredibly sophisticated sensors and integrated smart systems. And this evolution is fundamentally changing not only how we interact with light in our spaces, but also how we manage energy consumption, and even potentially how lighting can influence our mood or well-being.
Okay, let's start with the basics then and then move towards the more advanced stuff. The classic snap switch is probably what most people immediately picture when they hear the word switch. the standard flip switch.
Indeed. The snap switch is the quintessential light switch. It's manually actuated, typically by a mechanical lever, sometimes a handle, or often nowadays a rocking mechanism. It's also very commonly known as a toggle switch. That's the one you hear the classic click sound as it snaps into position. It physically stays in either the on or off position until you manually flip it back. It's a direct mechanical interruption or completion of the electrical flow to the light. Simple, reliable.
Okay, simple on-off. Then we get into controlling the amount of light, not just whether it's on or off. The dimmer switches, these are great, aren't they? For setting a mood or adapting the light level for different activities like watching a movie versus reading.
Yes, dimmer switches add a whole layer of flexibility. The sources mention the rotary dimmer switch, the kind you turn, or the slide type dimmer switch, the kind you slide up and down. These are specifically designed to control the amount of brightness of a light fixture, allowing you to adjust the light smoothly. From a very dim, subtle glow, all the way up to the bulb's full brightness output. This is fundamental, as you said, for setting mood, adapting light levels for different activities within the same room, and also for saving energy by only using as much light as is actually needed at that moment. It's worth noting again, though, with the prevalence of LEDs, using the right kind of dimmer is crucial. Older dimmers designed for incandescent bulbs often don't work well with LEDs. They can cause LEDs to flicker, buzz, or not dim smoothly or fully. Modern LED-compatible dimmers, often using different technology like trailing edge or ELV dimming, are needed for good performance.
Good tip. Okay, what about the push-button switch? That feels different from a toggle that stays put or a dimmer that adjusts level.
A push-button switch is fundamentally different because it's typically a momentary switch, or a non-latching switch, as the source calls it. Unlike a toggle switch that stays in the on or off position you leave it in, a push button only causes a temporary change in the state of an electrical circuit, only while the switch is physically actuated, meaning while you are actively pressing it down. As soon as you release it, it returns to its original default position, usually off. They're perfect for things like doorbells, where you only need a brief signal to activate the chime. Or they can be used in more complex lighting control systems, like smart systems, where a brief push might trigger a preset lighting scene. In many smart homes, a push button might not even be directly controlling the high voltage power to the light. Instead, it might just send a low voltage signal to a central controller, which then executes a complex lighting command, perhaps dimming multiple lights in the room to a specific level and changing their color temperature, all from one quick button press.
Okay, momentary action. Now, here's where it gets really interesting for, your everyday life and how lighting is becoming smarter and more intuitive. Motion detectors. We see these a lot in commercial buildings, like restrooms, but they're increasingly common in homes, too, inside and out.
Motion detectors are a prime example of intelligent, automated lighting control. They bring convenience and energy savings. They typically work by detecting the movement of heat sources, like our bodies, often using something called passive infrared, PIR technology, which senses changes in infrared radiation across its field of view. These devices provide both incredible convenience, the light just comes on when you walk in, and significant energy savings because the light only stays on when needed. Our sources suggest they work exceptionally well in locations like storage rooms, pantries, closets, laundry rooms, or hallways, places where lights might accidentally be left on, or where you might enter with your hands full. And outdoors, they are fantastic for enhancing security. They can automatically illuminate a porch, driveway, or backyard when someone approaches, which can discourage trespassing, vandalism, or theft. The light automatically turns on when motion is detected and then crucially turns itself off after a set period of no motion being detected, often adjustable. This ensures illumination only when and where it's needed, thus dramatically reducing wasted energy and simultaneously enhancing safety and security.
Yeah, I love the ones outside my house. Very practical. And along similar lines, sort of responding to the environment automatically, we have the photocell switch. This seems brilliant for outdoor lighting, just handling the dusk-to-dawn cycle automatically.
A photocell switch, sometimes called a dusk-to-dawn sensor, offers another layer of smart, automated, energy-efficient control, specifically reacting to ambient light levels. It's designed to control a fixture, or a group of fixtures, so that it turns on automatically when it gets dark outside, and then turns itself off again automatically when it senses sufficient ambient light, typically at dawn. This means your outdoor lights, maybe landscape lighting, pathway lights, or security lights, activate precisely when ambient light levels drop below a certain threshold, and then turn off again when the sun comes up, all without any manual intervention whatsoever. You set it and forget it. This further enhances energy savings by ensuring lights aren't left on during daylight hours and provides consistent security or pathway illumination throughout the entire night, adapting seamlessly to the changing length of days throughout the year. You'll see these very commonly integrated into streetlights or mounted on commercial building exteriors for signage or parking lot lighting.
Okay, so we've covered what the switch does on-off, dimming, momentary motion light sensing. But our sources also mention differences in how they're installed and, crucially, how many places you can actually control your lights from. It's not always just a single switch controlling a single light, right? That'd be inconvenient in many situations.
Precisely. The where and how many are just as important for usability. First, we can categorize switches by their installation method, which often impacts the final aesthetics and the practicality of the installation itself. Our sources mention flush-mounted switches. These are the most common type in modern construction. They are recessed into the wall, inside an electrical box. Only the switch mechanism and the cover plate are visible, offering a very clean, seamless look that integrates well with most interior designs. This requires cutting into the drywall or plaster and running the wiring hidden within the wall cavity. Then there are surface-mounted switches. These sit directly on the surface of the wall, often inside a protective box or housing. These might be used in situations where it's difficult or impractical to recess the wiring and box into the wall. For example, in older buildings with solid masonry walls, or maybe in garages, workshops, or basements with concrete walls. Sometimes surface mounting is also used when the wiring itself is run exposed on the surface, often inside protective tubing called conduit, which can be part of an industrial or loft aesthetic.
Okay, so flush-mounted is hidden in the wall, surface-mounted sits on top. That dictates how they look on the wall. But what about controlling lights from multiple locations? That's where the wiring gets really clever, isn't it? This is super useful.
This is a fundamental concept in both residential and commercial electrical wiring, and it vastly improves convenience and functionality in many common spaces. As the source material lays out, we have three main types of switches based on the number of locations they allow control from: the single pole, the three-way, and the four-way switch.
Okay, so what does this all mean for you, the listener, thinking about your own home? Think about a simple bedroom light versus, say, a long hallway or the lights over a staircase.
Let's use those exact examples. A single pole switch is the most basic and common type. It controls a light, a receptacle, like a switch to outlet for a lamp, or some other device from only one single location. That's it. So in your bedroom, you typically have one switch right by the door that turns the main overhead light on and off. That's usually a single pole switch. Power comes into the switch box, goes through the switch, when it's on, to the light fixture, and then the neutral wire carries the current back to the panel to complete the circuit. It's a simple interruption point on the hot wire.
Makes perfect sense. One switch, one point of control. Simple. But what if you have, like you said, a long hallway with a door at each end? Or a staircase with a light fixture in the middle? You definitely don't want to walk all the way down the dark hallway just to turn the light off after you've passed through. That'd be annoying.
That's precisely where the three-way switch comes in. Our sources state that these switches are always used in pairs. You need two of them. And they allow you to control a single light fixture or multiple fixtures wired together from two different locations. Interestingly, three-way switches don't have a simple on or off marking on the toggle itself because their position doesn't always indicate the state of the light. Instead, they work by routing the power between two special traveler wires that run between the two switch locations. So in your long hallway example, you'd have one three-way switch at one end and another three-way switch at the other end. You can turn the light on at the first switch when you enter, walk down the hall, and then turn the exact same light off from the second switch when you exit without needing to backtrack. Toggling either switch changes the state of the light on to off or off to on, regardless of the position of the other switch. It's incredibly convenient for hallways, stairways, rooms with two entrances.
Okay, that's the two-location solution. But what if you have an even larger space? Or maybe a room with multiple entrances, like a big living room or a kitchen with several doorways. Sometimes you need even more control points beyond just two. That's where the four-way switch makes an appearance, according to the source.
Exactly. For controlling a light from three or more locations, you need to add four-way switches into the mix. The rule is you always start and end the circuit with a three-way switch at the first and last control points. Then you place one or more four-way switches in between the two three-way switches for every additional control point you need. So imagine that large living room with entrances from the kitchen, a main hallway, and maybe a door to the patio. You could have a three-way switch at the kitchen entrance, another three-way switch at the patio entrance, and a four-way switch installed in the middle, perhaps near the hallway door. This setup would allow you to turn the main living room lights on or off from any of those three locations. If you had four entrances, you'd put two four-way switches in between the two three-ways. It's all about maximizing convenience and control in larger multi-access spaces, ensuring you never have to walk into a dark room or backtrack across a large area just to find a switch or turn off a light. It makes large spaces much more functional.
That makes total sense. Clever wiring. And finally, a simpler but still important aesthetic and organizational point mentioned. The number of switches per cover plate, often called gangs, right? You probably have a mix of these in your home without even realizing it. A single switch here, maybe two or three together there.
Yes, this simply refers to how many individual standard-sized switch devices or dimmers or outlets can fit neatly side by side onto one single cover plate mounted over the electrical box in the wall. Our sources mention the common configurations: 1 gang for a single device, 2 gang for 2 devices, 3 gang for 3, and 4 gang for 4. You can even find 5 or 6 gang plates sometimes, though they become quite large. It's purely about consolidating controls for a cleaner, more organized aesthetic on your wall. Instead of having, for example, 4 separate single switch plates clustered together for, say, the ceiling light, the fan, the under cabinet lights, and an accent light in your kitchen, you can have one neat 4-gang plate with all 4 switches or dimmers nicely aligned in a row. It's a small detail in the grand scheme, but it speaks to the thoughtful design that goes into both the functionality and the visual appeal of our built environments, reducing that visual clutter on the wall.
So we've truly taken a deep dive today, haven't we? We really covered a lot of ground. We started by unpacking the fundamental definitions, understanding that crucial difference between a lamp, the light source, and a luminaire, the whole fixture, and figuring out why lumens, brightness, and lux, light on a surface, matter so much more than just watts, energy use now. We then explored that monumental evolution of lamp technologies from the old workhorse fluorescent tubes through the transitional CFLs, the curly bulbs, and onto the truly revolutionary LEDs that are transforming efficiency, design possibilities, and maybe even our health.
Absolutely. Then we moved into the meticulous planning that goes into the hidden infrastructure, the circuit layout, seeing how architects and engineers use methods like the simple lumen method to ensure proper maintained illumination levels over time. And we delved into how critical guidelines, like that maximum fixture count per circuit, are put in place not just for functionality, but for fundamental safety and system stability, preventing overloads and fires.
And finally, we explored the surprisingly diverse world of control devices, the switches. Moving way beyond the simple on and off toggle to explore dimmers for mood control, momentary push buttons for smart triggers, and those clever automated options like motion sensors and photocells that add convenience and save energy. Plus, understanding the ingenious wiring behind 3-way and 4-way switches that gives us that essential control from multiple locations in our homes and buildings.
Yeah. The profound takeaway here, I think, is that understanding these fundamentals, even at this level, doesn't just make you incredibly well-informed about something you interact with constantly, every single day. It also really helps you appreciate the intentional, often invisible design and engineering that goes into every single illuminated space you enter. It's truly a testament to the complex systems, electrical, optical, mechanical, that seamlessly work together behind the walls and ceilings to create functional, efficient, safe, and even beautiful environments for us.
Absolutely. It really changes how you see things. So here's a thought for everyone listening. Next time you walk into a room and effortlessly flip a light switch, just take a moment. Pause for a second. Consider not just the light that immediately appears, but try to visualize that hidden network of meticulously planned wires snaking through the walls. Think of the carefully placed panel board somewhere in the building, acting as the central hub and the silent guardian. Consider the specific lamp technology inside that fixture, tirelessly converting electricity into photons. And appreciate the ingenious switch design right under your fingers, whether it's a simple mechanical toggle, a smooth dimmer slide, or maybe a smart sensor reacting to you or the daylight outside. All of it working together, seamlessly, reliably, and safely. What new questions might this spark for you about the built environment around you, about how these invisible systems were designed, and maybe how might these systems continue to evolve? With ever smarter technologies, maybe AI integration, and that growing focus on human-centric lighting designed to support our well-being in the years to come.
It's truly a system that never stops evolving, constantly adapting to our needs and our technological advancements. It's fascinating to watch. So yeah, go forth and look at the lights and switches in your own environment a little differently now. You'll definitely be surprised at what you start to notice now that you know what to look for.